She's the process engineer at CDAC Pune, and she's going to talk about the distributed deep learning training with Enroot on PARAM Rudra.
Hi everyone, and thanks for joining me today. I'm Sowmya Shree, and I'm a HPC AI engineer at the Center for Development of Advanced Computing, India. So today I'll be talking about distributed deep learning training using Enroot on PARAM Rudra systems. But before I do that, let me tell you a little about what we as an organization do. CDAC is a premier research and development organization of the Ministry of Electronics and Information Technology, Government of India. It was established in 1988 to address India's growing needs in areas like high-performance computing, artificial intelligence, quantum computing, digital communication, and many other fields. So, to address the growing compute demands across science and research, in 2015, the National Supercomputing Mission was initiated by the government to install supercomputers of various capacities in academic and R&D institutions across the country. Over the years, CDAC was able to deploy a number of clusters and also provide user support, maintain software stack, helping users to port their applications, to parallelize their codes and optimize their codes. Apart from the deployment, CDAC also conducts trainings and workshops and also offers various postgraduate diploma courses. So far, CDAC has deployed 19 systems as part of the NSM with a combined compute capacity of 32 petaflops. These supercomputing facilities support national level applications across various domains including genomics, drug discovery, flood forecasting, disaster management, weather modeling, telecom network optimization, material science, chemistry, and many other fields. Till date, we have around 10,000 plus HPC users, which includes 1,700 plus PhD students and 1,500 plus research publications made so far. More than 11 million HPC jobs have been executed till date. And coming to the human resource development part, we have trained around 26,200 human resources. CDAC is currently establishing PARAM Rudra state-of-the-art supercomputing systems across the country. These systems are based on Rudra servers designed, developed, and manufactured in India. Currently, they come with the NVIDIA A100 cards, which again can be customizable. These are the technical specifications of the PARAM Rudra cluster, which I conducted the current experiment on. It is deployed at the Inter-University Accelerator Center, New Delhi. The cluster consists of 4 types of nodes: the CPU-only nodes, GPU nodes with NVIDIA A100 cards, each node having 2 GPUs, then GPU-ready nodes, and high memory nodes for job executions that require higher memory. So the architecture diagram of Rudra systems looks something like this. The user logins to the cluster and lands on one of the login nodes among the 10. We have InfiniBand network for internode communication. We have 2 master nodes and 6 service nodes, internal network and BMC network for management purposes. Being an organization that deploys supercomputers across the country, there is a high need to make the systems AI ready, since everyone right now are talking LLMs and AI and chatbots. The traditional CPU-centric benchmarks won't give us any accurate picture of how our system will perform with real-world AI tasks. We need to ensure that the GPUs are not just present but fully utilized and integrated effectively within the system architecture. Next is the workload selection. We can't just pick any benchmark for AI readiness. We need to choose a benchmark that reflects the type of AI workloads we anticipate running. something like deep learning training benchmarks, for example, ResNet for image classification, which is widely known. So once we have our benchmarks, we move to the test configuration and execution. We need to configure our tests to simulate real-world AI scenarios. We execute these tests systematically, capturing detailed metrics on GPU utilization, memory usage, training time, and many other parameters. But what are the key benefits of doing all this? So, well, firstly, we can ensure that the system is truly delivering its full potential for AI workloads. It helps us identify stability issues that might only appear under intense AI workloads. But now the real problem is, if only executing on supercomputers was as easy as running it on your laptop. In reality, when we try to run these workloads, we face various challenges like environment conflicts, complex setups, poor scalability, and much more. But what if there was a better way? A consistent, portable, and a scalable way to train models on supercomputers. That's where containerization comes into the picture. Applications packaged in containers can run on any HPC system regardless of the underlying OS. It provides environment isolation, avoiding conflicts between different user dependencies. And it also simplifies the deployment of complex applications by just bundling the dependencies with the application itself. So let's take a moment to understand what capabilities are essential when we talk about containerized workflows in HPC and AI environments. So this particular slide summarizes NVIDIA's key motivations for container support in such settings. First and foremost thing is high performance is a non-negotiable factor. Containers must provide a near-native performance to be viable for HPC and AI workloads. Next is the support for Docker images. NVIDIA emphasized the need for compatibility with Docker images, which are like the de facto standard in many developer and research environments. Launching multi-node jobs, the container runtime should support seamless execution of MPI and other parallel applications across the nodes. And also the containers must allow full visibility of the GPUs, including the access to CUDA and other driver level components. So NVIDIA developed tools like NVIDIA Container Toolkit to solve issues like these. Next, coming to the resource isolation, containers must support isolation to ensure fair resource sharing and security. So this also includes like CPU cores, memory, GPU devices, and network bandwidth, especially on a shared HPC system. And the last point is the users often need to install new packages, test scripts, and debug code within the containers. So this feature is very important for research and development workflows. In summary, for containers to be truly effective in HPC and AI, they must combine performance, flexibility, and compatibility. NVIDIA's container ecosystem, especially with Enroot, addresses these exact needs, and that's what motivated their development in this direction. Enroot. Enroot is a lightweight containerization tool developed by NVIDIA specifically for HPC and AI workloads. Unlike traditional container platforms, Enroot is designed to be simple, secure, and efficient in shared cluster environments. So it works by transforming standard OS images into unprivileged sandboxes, which means that the users don't need to have root access, making it the ideal solution for multi-user HPC systems. To integrate Enroot with workload managers like SLURM, NVIDIA provides Pyxis, a plugin that allows users to run containers directly within SLURM jobs. Together, Enroot and Pyxis provide a powerful, flexible solution for running containerized applications at scale. So this slide compares Enroot Apptainer and Docker for HPC use. Enroot stands out because it doesn't require root access, has low overhead and integrates seamlessly with SLURM through Pyxis. It also offers a native GPU support, which is ideal for AI workloads. Aptainer, on the other hand, works well for HPC related workloads, and Docker, while popular, requires a root level daemon and has higher overhead and needs manual SLURM integration, making it less suited for shared HPC environments. So overall, Enroot with Pyxis offers the most secure and efficient option for HPC containerization. So the procedure followed to conduct the current experiment goes something like this. For prerequisites, we need Enroot installed in the cluster. Enroot was configured with Pyxis support. To build our environment, we downloaded the official PyTorch container from the NVIDIA's NGC catalog. So this container is already optimized for GPU performance and includes the libraries and dependencies we need for deep learning training. Next, we clone the deep learning examples repository provided by NVIDIA on GitHub. So this repository includes the best practice implementations of models like ResNet 50, and it's optimized for performance across NVIDIA hardware. Coming to the dataset, we have used the ImageNet, one of the most widely used datasets for image classification. We retrieved around 150,000 training images, which took up about 138 GBs, and 50,000 validation images, which took about 6.3 GBs. So the dataset spans 1,000 classes, so it's quite comprehensive and representative. We then pre-processed the dataset by extracting the tar files and labeling the training and validation images. This step is important to organize the data correctly before feeding it into the model itself. So for the model architecture, we use the ResNet 50, a deep convolutional neural network with 50 layers. It's well established model for image classification tasks. ResNet 50 expects a 224 cross 224 RGB images and uses the ReLU activation functions. The dataset was fairly balanced with around 1280 images per class, and we trained using the SGD optimizer with momentum, which helps in stabilizing and speeding up the convergence. We executed the training on PARAM Rudra to study scaling and performance. The containerized approach made this process consistent and reproducible across the runs. So as for the performance metric, we ran the training for 90 epochs, aiming for over 70% top 1 accuracy. We also recorded the training throughput to evaluate system efficiency and scaling. So coming to the methodology used to conduct this experiment, the user provides a configuration file specifying the training parameters. So the PyTorch image is imported and converted into a squash file. So squash file is something that the Enroot container supports. A bash script processes the configuration and initiates the master script through SLURM. In single node execution, the master script will launch a container and it will train the model. But in case of multi-node training, the master script spawns multiple slave scripts, and these slave scripts execute tasks within the Enroot containers built from the same squash file. So since it's distributed training and the model fits into the GPUs, data is distributed among GPUs and the model is replicated along all the GPUs and the training is performed. So this is the master SLURM script that submits the main job for distributed training. We requested one node with 2 GPUs and then extracted the head node host name to coordinate with the slave jobs. At the end, we use srun with the Enroot container image to run the actual training. It It mounts all the required directories and launches the training script using the multiproc.py, passing all the runtime arguments like model precision, batch size, and learning rate, and other parameters as well. So this is the slave script submitted by the master job to each additional node. It receives all runtime parameters like node rank, total nodes, model configuration, and data path, so each slave can correctly participate in the distributed training. Like the master, it uses srun to launch training inside the Enroot container. Each slave joins the multi-node training using its assigned node rank and communicates with the master node over the specified port to stay synchronized throughout the run. So coming to the results, if you look at the top right graph, you can see that the training time decreases as we add more GPUs, but eventually saturates. Now if we look at the throughput graph at the bottom, it's almost a straight line. That means that we are getting a near linear scalability. So coming to the conclusion, Enroot simplifies containerization for seamless deployment and efficient workload management on the PARAM Rudra system. Its tight integration with SLURM ensures optimal resource utilization, stable scaling, and high performance distributed training, which is critical for deep learning workloads. Unlike other container technologies like Docker, Enroot is lightweight, HPC and AI optimized, and eliminates unnecessary overhead. This makes it the ideal solution for running large scale AI training jobs efficiently on systems like PARAM Rudra. So, these are some of the reference links that I've used to prepare this presentation. That's all from my side. I'm happy to answer any questions.
Awesome. Thank you so much. Hello.
Hi.
So we can see, so not sure if you can see the feed, but so your face is quite big in the in the screen. Do we have any questions from the audience? How do you do distributed ML or artificial intelligence workloads in your cluster? That's a question for the audience. Okay. Well, so let me check in the Slack if we have any other question. And no, okay. So thank you so much for attending the event, for making this effort. Thank you so much.
Thank you.
Oh, yeah,
I really
okay.
want to thank. No, I really want to thank HPC-KP and the WHPC community for giving me this opportunity to present. Thank you so much.
All right. I have a quick question for you.
Okay.
I worked at NVIDIA in the past, and I was responsible for artificial intelligence, the training aspect, not the inference, at large scale.
Okay.
And I work in the benchmark, the industry benchmark called MLPerf. I don't know if you're
Yes.
familiar with it. So I was responsible,
we
for
do.
example, for the ResNet 50 runs with 2,000 GPUs competing against Google on the TPUs. And
Okay.
one of the things that I wanted to let you know is I know that you did the training of ResNet 50 in 90 epochs to reach the target
Yes.
accuracy. But
Yes.
through hyperparameter optimization, you can get it to converge in only 42 epochs, which is half the number of epochs. Obviously, in order to get to that type of acceleration on the training, which is important because you're reducing literally by half the amount of computing to hit the same accuracy, right? You do need to do the hyperparameter optimization, which it's doing a lot of training runs. But if you can leverage the existing hyperparameters, please do that, because then you will be saving a lot of computing time.
Okay, so I'm aware of MLPerf, but the only problem is that when we are trying to run these workloads and supercomputers, in our supercomputers, we do not give access for users to be added in the Docker group. So that would be a problem, like when it comes to running single node executions on supercomputers. But when it comes to multiple node executions, yes, I'm aware that SLURM with Pyxis implementations are available in MLPerf. I recently did execute the H100 submissions that was submitted by NVIDIA. This was one of the process followed for running it on our cluster, PARAM Rudra. But yes, definitely we are trying to run the MLPerf implementations on our servers. So we definitely want to submit it to the MLPerf community.
Okay, thanks.
Thank you.
Thanks again. Okay.